The question sounds like it should have a quick answer. Either something is infinite, in which case it has no edge, or it has an edge, in which case it is finite. That is how most people would reason about it, and that reasoning seems perfectly sound when applied to ordinary objects. A table has edges and is finite. The set of whole numbers has no edges and is infinite. The logic appears airtight. But the universe is not a table, and it is not a set of numbers. It is a physical system described by general relativity, governed by topology, shaped by the history of its own expansion, and observed from within by beings who can only see a limited portion of it. When all of those factors are taken into account, the seemingly simple question becomes remarkably subtle, and the answer is not what most people expect. To understand why, it helps to start not with the universe itself, but with the history of how people have thought about the concept of an edge. In ancient Greek cosmology, the universe was typically imagined as a bounded sphere. Aristotle placed the Earth at the centre, surrounded by nested crystalline spheres carrying the moon, the sun, the planets, and the fixed stars. The outermost sphere was the boundary of the cosmos. Beyond it, in Aristotle's framework, there was nothing, not even empty space. This was not a naive oversight. Aristotle had carefully considered the alternative. If the universe were infinite, he argued, there could be no natural place for anything, because an infinite space has no centre and no periphery, and without a centre, the physics of natural motion, in which heavy things fall toward the centre, would collapse. The edge of the cosmos was therefore not just an observational claim, but a structural necessity within his physical theory. The Epicureans disagreed. Lucretius, writing in the 1st century BCE, offered a famous thought experiment. Imagine standing at the supposed edge of the universe and throwing a javelin. Either the javelin continues onward, in which case the edge was not really the edge, or something stops it, in which case there is something beyond the edge, and again it was not the true boundary. This argument was meant to show that the universe must be infinite, because any proposed boundary could always be transcended. The argument is elegant, and versions of it have been reinvented many times throughout intellectual history, but it contains a hidden assumption that turns out to be physically important. It assumes that space is flat and extends in straight lines, that the javelin travels in a Euclidean trajectory, and that the concepts of beyond and farther always apply in the usual sense. These assumptions feel obvious, but they are not guaranteed by the laws of physics, and general relativity eventually revealed that they can fail. Between Lucretius and Einstein, the question of cosmic boundaries remained alive in European thought. Medieval scholars debated whether God could create space beyond the outermost sphere. Nicholas of Cusa, in the 15th century, argued that the universe has no circumference and no centre, anticipating in a philosophical sense the modern cosmological principle, though without the mathematical framework to make the idea precise. Giordano Bruno went further, proposing an infinite universe filled with an infinite number of worlds, and though he was burned at the stake in 1600 for a collection of heresies, the cosmological vision he articulated gained ground over the following centuries. By the time Newton formulated his theory of gravity, the prevailing assumption among natural philosophers was that the universe was probably infinite, because a finite universe with gravity pulling everything inward would seem to collapse into a single mass, whereas an infinite universe with matter spread evenly throughout would have no preferred centre of collapse. Newton himself recognized that this reasoning was not entirely stable, that an infinite homogeneous distribution of matter under gravity is in a precarious equilibrium, but the infinite model seemed less problematic than the finite alternative, and it persisted. The real breakthrough in understanding the relationship between infinity and edges came with the development of non-Euclidean geometry in the 19th century. Gauss, Bolyai, and Lobachevsky independently showed that Euclid's parallel postulate, the assumption that through a point not on a given line exactly one parallel line can be drawn, was not a logical necessity. Alternative geometries were consistent. On a sphere, for example, all lines that start out parallel eventually converge, and no parallel lines exist in the strict Euclidean sense. On a hyperbolic surface, shaped roughly like a saddle, infinitely many lines through a point can be drawn without ever intersecting a given line. These were not just mathematical curiosities. Gauss himself seems to have considered the possibility that physical space might be non-Euclidean, and he reportedly attempted to test this by measuring the angles of a large triangle formed by 3 mountain peaks, though the precision required was far beyond what his instruments could achieve. Riemann, in his famous 1854 habilitation lecture, took the idea much further. He introduced the concept of a manifold, a space that can be curved in arbitrary ways, and he distinguished between two properties that are often confused in everyday thinking. The first property is what mathematicians call the metric, which describes the local geometry, how distances and angles behave in a small neighbourhood of each point. The second property is the topology, which describes the overall global shape and connectivity of the space, whether it wraps around on itself, whether it has holes, whether it is simply connected or multiply connected. Riemann realized that these two properties are partly independent. A surface can be locally flat, meaning that small regions look exactly like a flat plane, and yet globally it can be rolled into a cylinder or a torus, giving it a completely different topology. This distinction is absolutely central to the question of whether the universe can be infinite and still have an edge, because it reveals that local geometric measurements cannot always determine global structure. When Einstein developed general relativity in 1915, he used Riemann's mathematics as the foundation. In general relativity, matter and energy determine the curvature of spacetime, and the curvature of spacetime tells matter and energy how to move. The famous field equations relate the geometry of spacetime, encoded in the Einstein tensor, to the distribution of matter and energy, encoded in the stress-energy tensor. Crucially, the field equations are local equations. They describe the relationship between curvature and matter at each individual point in spacetime. They do not by themselves determine the global topology. Two universes could obey exactly the same field equations, have exactly the same local geometry, and yet differ in their global shape because one is simply connected while the other wraps around on itself. This is not a theoretical speculation. It is a mathematical fact about the structure of the theory. Einstein himself grappled with the implications of this. In 1917, he applied his field equations to the universe as a whole for the first time, constructing the first relativistic cosmological model. He assumed that the universe was homogeneous and isotropic, meaning that it looks roughly the same at every point and in every direction, and he assumed that it was static, neither expanding nor contracting. To prevent the gravitational attraction of matter from causing the universe to collapse, he introduced the cosmological constant, a term in the field equations that acts as a kind of repulsive pressure counteracting gravity. The resulting model described a universe with the geometry of a three-dimensional sphere, often written as S3. This universe was finite in volume but had no boundary. It was the three-dimensional analogue of the surface of an ordinary sphere. Just as a two-dimensional creature living on the surface of a globe could travel in any direction, without ever reaching an edge, and yet would eventually return to its starting point, a three-dimensional being in Einstein's static universe could travel in any direction indefinitely, and would eventually circumnavigate the cosmos, and arrive back where it began. This was a profound conceptual step. It showed that a universe could be finite without having an edge. The answer to Lucretius's javelin argument was not that something blocks the javelin at the boundary, but that there is no boundary because the space curves back on itself. The javelin keeps going in a straight line, which in curved space is a geodesic, and eventually returns from the opposite direction. No edge is needed because the topology is closed. This resolved one of the oldest puzzles in cosmology, but it introduced a new one. If the universe is finite and closed, what determines its size? And does a finite closed universe necessarily have to be positively curved, like a sphere, or could other topologies also produce finite volumes? The answer to the second question is that many topologies can produce finite volumes, and they do not all require positive curvature. A three-dimensional torus, for example, can be constructed from a flat Euclidean space by identifying opposite faces of a cube. The local geometry is perfectly flat. Every triangle has angles summing to exactly 180 degrees, and yet the volume is finite, and there is no boundary. Light travelling in one direction would eventually return from the opposite direction, just as in a video game where going off one side of the screen brings you back on the other side. This is a flat, finite, edgeless universe. Similarly, there are topologies based on hyperbolic geometry that are finite and edgeless, despite having negative curvature. The classification of possible topologies for three-dimensional spaces is a rich area of mathematics, And the important point for cosmology is that the field equations of general relativity do not select a unique topology. The equations constrain the local curvature, but the global topology is an additional piece of information that must be determined observationally, if it can be determined at all. This brings the discussion to a crucial distinction that is often missed in popular accounts of cosmology. When cosmologists say the universe might be infinite, they're usually referring to the spatial geometry of a particular solution to the Friedmann equations, which are the simplified form of Einstein's field equations for a homogeneous and isotropic universe. If the average energy density of the universe is exactly equal to the critical density, which current observations suggest is the case to very high precision, then the spatial geometry is flat, meaning Euclidean, and the simplest flat topology is the infinite flat space R3, which extends without limit in all directions. But a flat universe does not have to be R3. It could be a torus, or a Klein bottle analogue, or one of the other 17 possible flat topologies classified by the Bieberbach theorems. Each of these is flat, consistent with all the same local measurements, but finite. So when observational cosmologists report that the universe appears to be spatially flat, they are giving information about the curvature, not the topology. The universe could be flat and infinite, or flat and finite, and distinguishing between these possibilities requires a completely different kind of observation. Now, the question posed at the outset asked whether the universe can be infinite and still have an edge. So far, the discussion has established that a universe can be finite without an edge, through closed topology, and that the local geometry alone does not determine whether the universe is finite or infinite. But the original question is about the combination of infinity and an edge, which seems contradictory but requires careful analysis. In the mathematical framework of general relativity, a spacetime manifold is defined as a topological space with certain smoothness properties and a metric. The manifold itself is the set of all spacetime points, and in standard cosmological models this manifold is taken to be complete and without boundary. The completeness condition, more precisely formulated in terms of geodesic completeness, means that every freely falling particle can be traced forward and backward in time indefinitely, or at least until it hits a singularity, which is a different kind of breakdown that will be addressed shortly. The absence of a boundary means that the manifold does not simply stop at some surface. There is no wall, no limit, no end of the grid. For an infinite universe modelled as R3 at each moment in time, this means that space genuinely extends without limit in all directions, and there is no edge anywhere. But the phrase, the edge of the universe, is used in popular science to mean something slightly different from a boundary of the manifold. It is often used to refer to the edge of the observable universe, which is a real and well-defined concept, but which has a completely different status from a physical boundary of space. The observable universe is the region of space from which light has had time to reach an observer since the Big Bang. Because the universe has a finite age, approximately 13.8 billion years, and because light travels at a finite speed, there is a maximum distance from which information could have reached any given observer. This defines a sphere around each observer called the particle horizon. For an observer on Earth, the particle horizon is currently at a moving distance of about 46.3 billion light-years in all directions. The fact that this number is larger than 13.8 billion light-years is a consequence of the expansion of space itself. Light emitted by a distant galaxy 13 billion years ago was emitted when that galaxy was much closer, and the expansion of the universe since then has carried it much farther away. The particle horizon is an edge of observation, not an edge of space. Beyond the horizon, space continues. Galaxies exist there. Physics operates by the same laws. We simply cannot see those regions because light from them has not had time to reach us. The horizon is observer-dependent. An observer in a galaxy 10 billion light-years from us has a different observable universe, partially overlapping with ours but centered on their own position. And the horizon changes with time. As the universe ages, light from more distant regions reaches us, and in a decelerating universe, the observable volume would grow steadily. In our actual universe, which is accelerating in its expansion due to dark energy, the situation is more complex. Some regions that are currently just inside our horizon will eventually fall beyond a new kind of horizon, the event horizon of the de Sitter space that our universe is approaching, meaning that events occurring in those regions will never be observable to us, no matter how long we wait. so the universe can be infinite, with no edge to space itself, while simultaneously presenting each observer with a very real and finite boundary of observational access. This is not a paradox. It is simply a consequence of combining infinite spatial extent with a finite age and a finite speed of light. The edge of the observable universe is real in the sense that it affects what we can know, measure and test, but it is not an edge of the universe in the sense that there is a wall or a boundary or a place where the fabric of space ends. But this answer, while correct as far as it goes, does not exhaust the question. There are deeper issues, and they emerge when one considers the nature of the Big Bang itself and the global structure of cosmological space-times. In the standard Friedmann-Lemaitre-Robertson-Walker models, the universe begins at a singularity. At time zero, the scale factor, which measures the size of the universe relative to its current size, is zero. Densities, temperatures, and curvatures are infinite. This singularity is not a point in space. It is a moment in time, the earliest moment, from which all subsequent evolution of the universe proceeds. The singularity is not part of the space-time manifold. It is a boundary of the manifold in the temporal direction. Geodesics traced back in time terminate there. They cannot be continued further. In this precise sense, the Big Bang is an edge of the universe, not a spatial edge, but a temporal edge, a past boundary of space-time beyond which the manifold does not extend. This temporal boundary exists regardless of whether the spatial sections of the universe are finite or infinite. In a flat, infinite universe described by the Standard Model, space at any given time after the Big Bang is infinite, extending without limit in all directions, and yet the entire space-time has a temporal beginning. An infinite universe emerged from a singularity. This statement requires careful interpretation. It does not mean that an infinite space was somehow concentrated at a single point and then expanded outward. That is a common misconception fostered by some popular accounts. Rather, in the mathematical model, at every time after time zero, space is already infinite. The scale factor was smaller in the past, which means that the distances between any two co-moving points were smaller, but if space was infinite at any time, it was always infinite, all the way back to the arbitrarily early moments after the singularity. The singularity itself is a limit that is approached but never reached within the manifold. The universe did not expand from a point into infinity. It was always infinite, just denser and hotter at earlier times. Whether this mathematical picture accurately describes the real universe near the moment of the Big Bang is a separate question, and one where current physics reaches its limits. General relativity predicts the singularity, but general relativity is a classical theory. It does not incorporate quantum mechanics. At the extremely high energies and small distances relevant to the very early universe, the Planck scale, where quantum gravitational effects are expected to become important, the classical equations of general relativity are no longer trustworthy. The singularity may be an artifact of using a theory beyond its domain of validity. Theories of quantum gravity, such as loop quantum gravity, and certain approaches within string theory, suggest that the classical singularity might be replaced by a bounce, a phase in which a previously contracting universe reaches a minimum size and then begins expanding. If such a bounce occurred, then the temporal edge of the universe, the Big Bang singularity, would be removed, and spacetime might extend to the past of what we currently call the beginning of the universe. The universe might have no temporal edge at all, having existed in some form for an infinite past, cycling through contractions and expansions, or transitioning from a qualitatively different prior phase. These are active areas of research, not settled conclusions. The point for the present discussion is that the concept of an edge of the universe is not limited to spatial boundaries. It can also refer to temporal boundaries, and the question of whether those temporal boundaries are genuine features of the universe or artifacts of incomplete theories is one of the most important open problems in theoretical physics. Now, returning to the spatial question, there is another possibility that sometimes comes up in more technical discussions, and that is worth exploring here. Can a spatial manifold be infinite and still have an edge in some meaningful sense? In standard general relativity, the manifold is assumed to be without boundary, meaning there is no set of points at the border of the manifold where spacetime simply stops. But what happens if one relaxes this assumption? Can space-time have a genuine boundary, a place where space-time itself ends, beyond which there is nothing? The answer depends on what one means by nothing. In general relativity, the manifold is the totality of space-time. There is no embedding space in which the manifold sits. The universe is not a ball floating in a larger room, it is the entirety of physical reality. So when mathematicians say the manifold has no boundary, they mean that the manifold is a complete description and that there are no missing pieces. But one could, in principle, construct a mathematical space-time that has a boundary, a surface, beyond which the manifold is not defined. Such a space-time would be physically peculiar, because particles reaching the boundary would simply cease to exist, not by being destroyed by any physical process, but by running out of space-time to exist in. This would violate the principle that physics should be deterministic, that the laws should uniquely determine the future of any physical system. If particles can reach the edge of space-time in a finite amount of their own proper time, then the equations of motion have no answer for what happens next. This kind of geodesic incompleteness is exactly what characterizes singularities in general relativity, and the singularity theorems of Penrose and Hawking demonstrate that under physically reasonable conditions, singularities are unavoidable. This is a subtle and important point. The singularities of general relativity, including the Big Bang and the interiors of black holes, are precisely places where space-time has an edge, where geodesics terminate, where the manifold breaks down. They are not part of the manifold, they are missing points, gaps in the fabric of space-time that the theory cannot fill. In this technical sense, the universe does have edges, at singularities, even if it is spatially infinite. These edges are not spatial boundaries in the usual sense. They are places where the curvature becomes infinite and the smooth structure of the manifold fails. But they are genuine breakdowns of space-time, and they are predicted by the theory itself. The relationship between these singularity edges and the question of infinite spatial extent is not contradictory. A spatially infinite universe can contain singularities, both the initial singularity of the Big Bang and the singularities inside black holes. These are isolated temporal or space-like boundaries within an otherwise boundaryless manifold. The universe is infinite in spatial extent at any given moment after the Big Bang, but the manifold as a whole, considered as a four-dimensional space-time, has boundaries in the form of singularities. Whether these boundaries should be called edges is partly a matter of definition, but they certainly function as limits of the physical description, places where prediction fails and new physics is needed. This leads to a discussion of a concept that is important for making the question precise, the distinction between a boundary and an edge in the topological sense. In topology, a manifold with boundary is a space where some points have neighborhoods that look like half spaces rather than full spaces. Think of a disk. Interior points have neighborhoods that are full circles, but points on the rim have neighborhoods that are half circles. The rim is the boundary. A manifold without boundary, like a sphere or a torus, has no such special points. In general relativity, space-time is always modeled as a manifold without boundary. Singularities are not included in the manifold, they are removed from it. So in the strict mathematical sense, the space-time manifold of general relativity is boundaryless, even when singularities are present. The singularities are not edges of the manifold, they are missing from the manifold. This might seem like a technicality, but it has physical consequences. It means that the universe, as described by general relativity, never has a spatial edge in the topological sense, regardless of whether it is finite or infinite. But there are other frameworks in which boundaries of space-time are allowed. In string theory, for example, space-time can have boundaries in the form of orientifold planes and D-branes, which are extended objects on which open strings can end. The boundaries in these models are not places where space-time ceases to exist, but rather dynamical objects with their own physical properties. In the ADS/CFT correspondence, a major theoretical development in string theory, a gravitational theory in a bulk spacetime, is equivalent to a non-gravitational theory on the boundary of that spacetime. The boundary in this case is a conformal boundary at infinity, not a physical wall, but it plays a fundamental role in defining the theory. These examples show that in more general theoretical frameworks beyond classical general relativity, the concept of a boundary of spacetime is richer and more varied than one might initially expect. Let us now turn to a different approach to the question, one that involves the topology of the universe and the possibility of detecting it observationally. If the universe is finite but has no boundary, its finite topology might leave observable signatures. The most discussed such signature involves the cosmic microwave background radiation, the CMB, which is the oldest light in the universe, emitted approximately 380,000 years after the Big Bang, when the universe cooled enough for neutral atoms to form and the plasma that filled the universe became transparent. The CMB comes to us from a spherical surface called the last scattering surface, which is at a specific distance in all directions. If the universe is finite and smaller than the distance to the last scattering surface, then light from the CMB could have wrapped around the universe, and we would see the same physical region of space from different directions. This would produce match patterns in the CMB, specific correlations in the temperature fluctuations that would betray the topology. The search for these matched circles in the CMB data has been carried out using observations from the WMAP satellite and the Planck satellite. The results have been largely negative. No convincing evidence for a finite topology has been found at scales comparable to or smaller than the observable universe. This places a lower limit on the size of any compact dimension of the universe. If the universe is a 3 torus, for example, the size of the torus must be significantly larger than the diameter of the observable universe for its topology to be undetectable in the CMB. This means that even if the universe is finite, its size is at least several times the size of the observable universe, and possibly much larger. Of course, this does not rule out a finite universe. It merely means that the finite topology is too large for us to detect with current methods. There is an additional subtlety here that relates to the question of edges. Even if the universe is finite with a complicated topology, it would still have no edge. The topology would be compact, meaning that one could travel in a straight line and eventually return to one's starting point, but at no point during the journey would one encounter a wall, a barrier, or a place where space ends. The finite universe wraps around, and the journey is seamless. This is the generic situation for compact manifolds without boundary. They are finite in volume but edgeless. The concept of an edge in the ordinary sense simply does not apply. So to this point, the analysis suggests the following answers. In standard general relativity, the universe can be infinite, with no spatial edge, or it can be finite, also with no spatial edge, if its topology is compact. In both cases, the manifold is without boundary. The observable universe has an edge, the particle horizon, but this is not a physical boundary of space. The Big Bang singularity is a temporal edge where space-time begins, and singularities inside black holes are space-like boundaries where space-time ends. But these are not included in the manifold and do not function as spatial edges that one could encounter by travelling far enough. But there is still more to say, because the question also touches on the concept of infinity itself and how it relates to physical reality. This is a subject with a deep history in philosophy and mathematics that has practical implications for cosmology. The concept of actual infinity, the idea that a completed infinite collection can exist as a realized totality, was controversial in Greek philosophy. Aristotle distinguished between potential infinity, which is a process that can always be continued further, and actual infinity, which is a completed infinite quantity. He accepted the former but rejected the latter. A line can be extended indefinitely, but it is never actually infinitely long at any moment. This Aristotelian view dominated Western thought for centuries and was only challenged in the 19th century by Georg Cantor, who developed the mathematical theory of transfinite numbers and showed that infinite sets could be rigorously defined, compared, and manipulated. Cantor demonstrated, for instance, that the set of real numbers is larger than the set of natural numbers, in the precise sense that no one-to-one correspondence exists between them. His work was initially met with fierce opposition from mathematicians like Kronecker, who considered the actual infinite to be mathematically illegitimate, but it eventually became the foundation of modern set theory, and by extension, of modern mathematics. In physics, the question of whether infinity is physically realized, as opposed to being merely a mathematical idealization, remains open and contested. The standard cosmological models, as discussed earlier, allow for a spatially infinite universe. But asserting that the universe is spatially infinite is an extraordinary claim, because it means that the number of galaxies, the number of atoms, the number of physical events, is genuinely infinite, not just very large. This has consequences that some physicists find unsettling. In an infinite universe with the same statistical properties everywhere, every possible configuration of matter that is consistent with the laws of physics would be realized somewhere, not just once, but infinitely many times. This means there would be infinitely many copies of every galaxy, every planet, every person, every brain, spread throughout the infinite volume. This is not a speculative extrapolation, but a straightforward consequence of combining the assumption of spatial infinity with the assumption of statistical homogeneity. If every possible configuration occurs somewhere, then every possible observation is made by some observer, and the concept of making predictions from observations becomes deeply problematic, because there is no way to distinguish our observation from the identical observation made by one of the infinitely many copies of us in distant regions. This difficulty is known as the measure problem in cosmology, and it is one of the most serious conceptual problems in modern theoretical physics. It arises most acutely in the context of eternal inflation, a version of the inflationary theory of the early universe, in which inflation never ends globally but continues forever, creating an infinite number of pocket universes with potentially different physical properties. In eternal inflation, the multiverse is genuinely infinite, and the question of what is typical, what is likely, what should be predicted, becomes mathematically undefined without a choice of measure, a way of assigning relative weights to different outcomes. Different choices of measure lead to different predictions, and there is no consensus on which choice is correct. Some physicists regard this as a sign that the theory of eternal inflation is incomplete, or even that the assumption of infinity is physically wrong. Others accept the measure problem as a genuine difficulty, but hope that it can be resolved by further theoretical work. The relevance of this to the question of edges is indirect but important. If the universe is truly infinite, it has no spatial edge. But if the assumption of infinity leads to conceptual or predictive difficulties that cannot be resolved, this might be taken as indirect evidence that the universe is in fact finite, even if it is much larger than the observable region. A finite universe with compact topology would avoid the measure problem, because the total number of galaxies and observers would be finite, and statistical reasoning would proceed in the usual way. The choice between infinity and finitude is therefore not just a question of geometry or topology. It has implications for the logical and epistemological foundations of cosmology. There is a related concept that deserves attention here, which is the idea of a conformal boundary. In mathematical physics, it is often useful to add boundary points to a spacetime that is technically infinite in extent. This is done by performing a conformal transformation, a rescaling of the metric that shrinks infinite distances to finite values. The resulting compact space includes the original spacetime plus additional points at infinity, which collectively form the conformal boundary. This technique was developed by Penrose and is widely used in the study of the global structure of spacetimes, which is visualized using Penrose diagrams. In a Penrose diagram, the entire infinite spacetime is compressed into a finite drawing, with the conformal boundary appearing as the edges of the diagram. For the simplest cosmological models, the conformal boundary has a clear interpretation. For de Sitter space, which is the spacetime of a universe dominated by a positive cosmological constant, and is the state our universe is approaching, the conformal boundary at future infinity is a space-like surface. This surface represents the infinite future of the universe. It is not a physical barrier, but a mathematical representation of the fact that the universe expands forever. For anti-de Sitter space, which has a negative cosmological constant, and is the setting for the ADS/CFT correspondence, the conformal boundary is a time-like surface, and it plays a fundamental role in the physics. The quantum field theory that lives on the boundary encodes all the physics of the gravitational theory in the bulk. In the ADS/CFT framework, the boundary is not just a mathematical convenience, but a physical object, in the sense that a complete description of the physics can be given in terms of the boundary theory alone. This is a genuinely remarkable result. It suggests that in at least some theoretical settings, a space-time that is infinite in extent can be fully described by a theory that lives on a finite boundary. The information content of the infinite bulk is entirely captured by the finite boundary. This idea, known as the holographic principle, has been enormously influential in theoretical physics, and it raises deep questions about the meaning of spatial extent and the relationship between volume and information. If the physics of an infinite space can be encoded on a finite boundary, then in what sense is the space truly infinite? Is the infinity real, or is it an artifact of one particular description, a kind of redundancy that is removed when one passes to the more fundamental boundary description? These questions do not have settled answers, and they illustrate how the concepts of infinity, finiteness, and edges become entangled in subtle ways when pushed to their theoretical limits. Let us now consider yet another sense in which the universe might have an edge, one that is less often discussed in popular accounts, but that is physically significant. This involves the possibility of a cosmological horizon that acts as a causal boundary, dividing the universe into regions that can communicate with each other and regions that cannot. In a universe dominated by dark energy, as ours appears to be, the expansion of space accelerates over time. This acceleration means that distant galaxies are receding from us at ever-increasing rates, and galaxies that are currently beyond a certain distance are receding faster than the speed of light. Now, the statement that galaxies can recede faster than light is often misunderstood. It does not violate special relativity, because the recession is not a motion through space but an expansion of space itself. Special relativity forbids faster than light travel through space, but says nothing about the rate at which space itself can expand. Nevertheless, the practical consequence is that light emitted by these very distant galaxies will never reach us. They are beyond our cosmological event horizon. The cosmological event horizon is different from the particle horizon discussed earlier. The particle horizon is the boundary of the region from which light has already reached us. The event horizon is the boundary of the region from which light will ever reach us, given the future evolution of the universe. In a universe that accelerates forever, the event horizon is a fixed, co-moving distance, and it is closer than the particle horizon. As the universe ages, the particle horizon grows, but the event horizon stabilizes. Galaxies that are currently between the event horizon and the particle horizon are visible to us now, but will eventually fade from view as their light is stretched to infinite wavelength by the expansion. In the very far future, observers in our galaxy will see an increasingly empty sky, with only the local group of gravitationally bound galaxies remaining visible. The rest of the universe will have disappeared beyond the event horizon, never to be seen again. This is a kind of edge, in the sense that it marks a fundamental limit on our causal interaction with the rest of the universe. But it is not an edge of the universe itself. The universe continues beyond the event horizon, filled with galaxies and stars and physics, but that region is causally disconnected from us. We cannot send signals there, and signals from there cannot reach us. The universe as a whole is edgeless, but the universe as accessible to any particular observer has a definite and shrinking boundary. This is a situation in which the universe is infinite and edgeless in its totality, but finite and bounded in its observational and causal reach. The interplay between these different kinds of horizons and boundaries, particle horizon, event horizon, Hubble sphere, light cone, conformal boundary, creates a rich structure that is easy to confuse when discussed casually, but that is precisely defined within the framework of general relativity. Each type of horizon answers a different physical question. The particle horizon answers, from how far away has information had time to reach us? The event horizon answers, from how far away will information ever reach us? The Hubble sphere answers, at what distance is the recession velocity equal to the speed of light at this moment? These are all different surfaces, at different distances, and they all change with time. None of them is an edge of the universe. They are all edges of our relationship with the universe, limits on our knowledge, our causal influence, and our observational access. Understanding this distinction is essential for answering the original question honestly. The universe can be infinite and still present us with multiple effective edges, all of which are observer-dependent and none of which is a boundary of space itself. The edges are in our perspective, not in the cosmos. There is one more theoretical context in which the question of edges and infinity takes on a different character, and that is the scenario of cosmological inflation and its implications for the global structure of the universe. Inflation is a period of exponentially rapid expansion that is hypothesized to have occurred in the very early universe, within a tiny fraction of a second after the Big Bang. During inflation, a microscopically small region of space was stretched to enormous size, smoothing out any initial inhomogeneities and flattening the spatial geometry. Inflation explains why the observable universe is so homogeneous, and why it is so close to spatially flat. Two features that would otherwise require extremely fine-tuned initial conditions. But inflation has a further consequence that is less well known and more speculative. In many versions of inflationary theory, inflation does not end everywhere at once. Instead, it ends in local regions called pocket universes or bubble universes, where the inflaton field, the hypothetical field driving inflation, decays to a lower energy state. Between these pockets, inflation continues, and because inflation is exponential, the inflating regions grow faster than the pockets can fill them. The result is a fractal-like structure in which pockets of post-inflationary universe are embedded in a continually inflating background, and this process continues forever into the future. This is eternal inflation mentioned earlier, and it produces a multiverse, an infinite collection of pocket universes, each potentially with different physical constants, particle physics, and even different effective dimensionality. In the context of eternal inflation, each pocket universe can be infinite in its own interior, because the geometry inside a bubble is described by an open Friedman model, which has infinite spatial extent. So the multiverse is infinite at two levels. It contains infinitely many pocket universes, and each pocket universe is itself spatially infinite. The question of edges becomes remarkably complex here. Each pocket universe has no spatial edge. It is an open, infinite space within a bubble. But the bubble has a boundary, the bubble wall, which separates the interior from the still inflating exterior. From the inside, the bubble wall is not at a finite distance. It is at infinite space-like distance thanks to the open geometry. But from the outside, from the perspective of the inflating background, the bubble is a bounded object, nucleated at a specific location and expanding at the speed of light. So is the bubble wall an edge of the universe? From inside, no, because it is unreachable in finite time and the space inside is infinite and self-contained. From outside, the bubble is a bounded object in an infinite inflating space. The concept of an edge depends on the reference frame, the coordinate system, and the notion of distance one uses. This is a more extreme version of the observer-dependent horizons discussed earlier. In eternal inflation, the very question of whether the universe has an edge becomes contingent on which part of the multiverse one considers, and even on the definition of the universe. This proliferation of meaning is not a defect of the theory. It reflects the genuine physical complexity of the situation. The universe, as described by modern theoretical physics, is not a simple thing with a simple answer to the question of its boundaries. It is a structure that can be finite or infinite, bounded or unbounded, singular or smooth, depending on the scale, the epoch, and the theoretical framework. The question, can the universe be infinite and still have an edge, has multiple answers, each correct within its own context. In the context of spatial topology, an infinite universe with the standard R3 topology has no spatial edge. A finite universe with compact topology also has no spatial edge. In both cases, the manifold is without boundary. Spatial edges do not occur in standard general relativistic cosmology. In the context of temporal boundaries, the Big Bang singularity is a temporal edge of space-time, a past boundary where the classical description fails. If quantum gravity resolves the singularity, this edge may not be fundamental. Similarly, if the universe recollapses in the distant future, a Big Crunch singularity would be a future temporal edge. But current observations suggest the expansion is accelerating, and the universe will expand forever, so no future temporal edge is expected in standard cosmology. In the context of singularities, black hole singularities are edges of space-time inside black holes, where geodesics terminate. These are localized edges, not global boundaries. They coexist with the global infinity of the spatial manifold. In the context of observational horizons, the particle horizon and the event horizon are effective edges of the observable and causally accessible universe, but they are not edges of space. They are properties of the observer's relationship to the rest of the universe. In the context of conformal boundaries, the conformal boundary at infinity is a mathematical construction that compactifies the spacetime, adding idealized points at infinity. It is not a physical edge, but a theoretical tool. In the ADS/CFT framework, however, the conformal boundary takes on physical significance as the locus of the dual field theory. In the context of eternal inflation, bubble walls are boundaries between different phases of the multiverse but from the inside of a bubble, the wall is infinitely far away and the space is infinite. The concept of an edge depends entirely on the perspective. Each of these answers is self-consistent, and each addresses a different aspect of the original question. The universe can be infinite in spatial extent and simultaneously possess temporal boundaries, contain singularities, be bounded by observational horizons, and be situated within a larger multiverse with its own boundary structures. None of these boundaries are the kind of edge that a table has, a place where the object stops and something else begins. They are subtler, more varied, and more context-dependent. There is a deep reason why this question is so difficult to answer simply, and it has to do with the distinction between intrinsic and extrinsic descriptions of space. When we think about the edge of a table, we're thinking extrinsically. The table is an object embedded in a room, and the edge is where the table ends and the room's air begins. This requires a larger space in which the table sits, but the universe, by definition, is not embedded in anything larger. There is no outside in which the universe is situated. The universe is all there is, at least in the classical general relativistic framework. This means that the concept of an edge, as a place where one kind of thing ends and another kind of thing begins, does not straightforwardly apply. An edge requires something beyond it, and if there is nothing beyond the universe, there can be no edge in the extrinsic sense. This does not mean, however, that the intrinsic structure of the universe cannot have features that function like edges. The singularities, the horizons, and the conformal boundary are all intrinsic features, defined without reference to any external space. They are part of the internal structure of the space-time manifold, and they represent genuine limits, places where physical description changes character, breaks down, or becomes inaccessible. They are edges in a generalized sense, and they can coexist with spatial infinity. The history of how these ideas developed reveals how deeply they are connected to the evolution of mathematics and physics. The development of non-Euclidean geometry made it possible to imagine finite spaces without edges. The development of general relativity made it possible to model such spaces as physical spacetimes. The development of observational cosmology made it possible to test whether the universe is flat, open or closed, and to place limits on its spatial topology. The development of inflationary theory raised the possibility that the observable universe is a tiny fraction of a much larger, possibly infinite, and possibly structured whole. And the development of quantum gravity, still ongoing and incomplete, promises to address the nature of the singularities that represent the most fundamental edges of spacetime. At each stage, the question, "Does the universe have an edge?" was answered differently. Not because the physical reality changed, but because the concepts used to describe that reality became more refined. The Aristotelian cosmos had a definite spatial edge. Newton's universe was probably infinite and had no edge. Einstein's static universe was finite but edgeless. The standard Big Bang model is possibly infinite and has a temporal edge at the singularity. The inflationary multiverse is infinite in multiple ways and has a proliferation of boundary-like structures. And the eventual theory of quantum gravity may eliminate all edges entirely, or it may reveal new kinds of boundaries that are not yet imagined. It is worth pausing to consider the epistemological situation more carefully. All of the statements made above about the universe's spatial extent, its topology, its boundary structure, and its global properties are based on theoretical models that are constrained, but not fully determined, by observational data. The observations tell us that the universe is very nearly spatially flat, that it is homogeneous and isotropic on large scales, that it is expanding at an accelerating rate, and that the cosmic microwave background has a pattern of fluctuations consistent with inflationary predictions. From these observations, combined with the theoretical framework of general relativity and the standard model of particle physics, cosmologists construct models of the universe. But the observations only constrain the local properties of the universe, the region within our particle horizon. The global properties, the total size, the topology, the presence or absence of boundaries beyond our observational reach are not directly constrained by any observation. They are inferred, or sometimes assumed, based on theoretical considerations such as simplicity, consistency, and naturalness. This means that the answer to the question, "Can the universe be infinite and still have an edge?" is not solely a matter of observation. It is partly a matter of theoretical framework, of which concepts are used and how they are defined. In one framework, the universe is infinite and edgeless. In another, it is finite and edgeless. In yet another, it is infinite with temporal edges. And in speculative extensions, it may have entirely new kinds of boundaries. The question is not ambiguous because it is poorly formulated. It is ambiguous because the concepts of infinite and edge have multiple precise meanings in the relevant physical and mathematical theories, and different combinations of these meanings lead to different answers. One can also approach the question from the perspective of mathematical logic and set theory. In mathematics, the real number line is infinite and has no endpoints. It extends without bound in both directions. But the real number line can be compactified by adding 2 points, positive infinity and negative infinity, to create the extended real line, which is compact and has endpoints. Alternatively, the real line can be wrapped into a circle by identifying its two ends, creating a space that is finite and without boundary. Each of these constructions is valid, and each captures a different aspect of the idea of adding an edge to an infinite space. In topology, the notion of a one-point compactification takes any non-compact space and adds a single point at infinity to make it compact. This is a powerful mathematical technique, but it does not correspond to a physical process of adding a boundary to the universe. It is a change in the mathematical model, not a change in physical reality. The physicist's question then is not, can we mathematically add an edge to an infinite space? Because the answer to that is trivially yes. The question is, does the physical universe, as described by the best available theories and constrained by the best available observations, possess an edge in any physically meaningful sense? And the answer, as this long exploration has shown, is nuanced. There are physical features of the universe, singularities, horizons, conformal boundaries that function as limits, boundaries, and edges in various generalized senses. These features can coexist with spatial infinity. The universe can be, and in the standard model almost certainly is, infinite in spatial extent while simultaneously possessing temporal boundaries and observational limits that give it the appearance of finiteness to any particular observer. The resolution of the apparent paradox in the original question lies in recognizing that the intuitive concept of an edge is a compound concept, mixing together several distinct ideas. The spatial boundary of an object, the limit of what can be observed, the breakdown of physical description, and the beginning or end of time. In everyday experience, these are all encountered together because everyday objects have spatial boundaries, are fully observable, are well described by physics, and persist for finite times. But the universe is not an everyday object. Its properties can come apart in ways that everyday experience does not prepare us for. The universe can be spatially infinite and have no spatial boundary, while having a temporal boundary at the Big Bang. It can be spatially infinite and have no spatial boundary, while being only partially observable due to causal horizons. It can be spatially infinite and have no spatial boundary, while containing localized singularities that function as internal boundaries of the spacetime structure. The question, can the universe be infinite and still have an edge, therefore has the answer, yes. But the edge in question is not the kind of edge that common intuition imagines. It is not a wall at the end of space beyond which there is emptiness or nothingness. It is a boundary of a different kind, temporal, causal, informational, or structural, and it is not in contradiction with spatial infinity. The universe can extend without limit in every spatial direction and still have an origin in time, still have horizons that limit observation, still have singularities that bound the description, and still have conformal boundaries that encode its physics. These are all types of edges, and they are all compatible with infinity. This conclusion is not a simplification or a tidying up. It reflects the genuine complexity of the physical situation. The universe is a more varied and more intricate structure than any single intuitive concept can capture. The notions of infinite and edge are both richer than everyday language suggests, and when applied to the universe, they must be used with the precision that physics and mathematics demand. The history of cosmology is, in large part, the history of learning to make these distinctions, and the process is not yet complete. New theoretical developments and new observational data will continue to refine, challenge, and perhaps transform our understanding of the universe's boundaries, its extent, and the relationship between the two. One of the reasons this topic is so persistent in popular interest is that it touches on something fundamental about the human relationship to the cosmos. The question of whether there is an edge to the universe is, at bottom, a question about limits. Are there limits to what exists? Limits to where one can go? Limits to what can be known? The answers that physics provides are not always comforting and not always intuitive, but they are always informative. They tell us that the universe is bigger than we can see, possibly bigger than anything we can imagine, and that our position within it is not at a centre, not at an edge, but simply somewhere, a generic location in a cosmos that may have no special locations at all. The journey from Aristotle's bounded cosmos to the modern infinite edgeless universe, or rather to the modern infinite universe with its subtle hierarchy of boundaries and limits, is one of the great intellectual achievements of human civilization. It required the invention of new mathematics, the development of new physics, the construction of extraordinary instruments, and the willingness to abandon intuitions that had served well in everyday life, but failed when applied to the cosmos. And the journey is ongoing. The questions that remain open about the nature of singularities, the topology of space, the measure problem in eternal inflation, and the correct framework for quantum gravity are among the deepest in all of science. Their resolution will determine whether the universe has an edge in senses that are not yet conceived, or whether it is truly in every sense without limit. Each new instrument, each new theoretical framework, and each new piece of observational data adds a small refinement to this picture. The Planck satellite's precise measurements of the cosmic microwave background push the lower limit on the size of any compact spatial dimension farther out, making the observable universe a smaller fraction of the whole if the universe is indeed finite. Gravitational wave observations from LIGO and Virgo probe the structure of space-time near black holes, approaching the regime where singularity edges might reveal new physics. Proposals for space-based gravitational wave detectors like LISA will extend this reach. Theoretical advances in loop quantum gravity and string theory continue to explore whether singularities are genuine features of nature or artifacts of incomplete theories, and the eventual detection, or non-detection, of primordial gravitational waves from inflation will constrain the energy scale at which inflation occurred, bearing indirectly on the question of whether eternal inflation, with its infinite multiverse and its proliferating boundaries, is the correct picture of the larger scale structure of reality. The interplay between theory and observation in cosmology is unlike that in any other science, because the object of study is unique, unrepeatable, and observed from the inside. There is only one universe, and it cannot be put in a laboratory. Its largest scale properties are constrained by observations made from a single vantage point, within a single horizon, over a tiny fraction of its total history. And yet, the combination of precise observations, powerful theoretical frameworks, and rigorous mathematical tools has allowed cosmologists to construct a remarkably detailed and consistent picture of the universe's history, composition, and geometry. The question of edges and infinity sits at the intersection of all these efforts, and it is a question that every new advance helps to sharpen, even if it does not fully resolve it. What emerges from this entire discussion is not a single, definitive answer, but a map of the conceptual landscape surrounding the question. The landscape is rich, varied, and still being explored. Some regions are well charted. The distinction between finite and infinite spatial geometries, the role of topology, the nature of observational horizons. Other regions are less well understood. The physics of singularities, the interpretation of the multiverse, the relationship between information and spatial extent in holographic theories. And some regions are essentially unexplored, waiting for theoretical breakthroughs that may not come for decades or generations. In this landscape, the question, can the universe be infinite and still have an edge, is not a paradox to be resolved, but a probe, a tool for exploring the deepest features of physical reality. The answer, in brief, is that the universe can be infinite in spatial extent while possessing edges of a non-spatial kind, including temporal boundaries, causal horizons, singularities, and conformal boundaries. These edges do not contradict the infinity of space. They complement it, adding structure and richness to a cosmos that is far more complex than any simple picture of infinite, edgeless space can convey. The details of this complexity are not mere academic refinements. They have practical consequences for what we can observe, what we can predict, and what we can hope to understand. The particle horizon determines the maximum amount of data available to cosmology. The event horizon determines the maximum amount of data that will ever be available. The topology of space determines whether patterns might repeat on the sky. The nature of singularities determines whether the laws of physics are complete, and the structure of the multiverse, if it exists, determines whether our universe is typical or unusual, and whether the values of physical constants can be explained or must simply be accepted. Each of these issues is, in its own way, a question about edges of knowledge, edges of prediction, edges of explanation, and each connects back to the original question about whether an infinite universe can have an edge, because each reveals a different dimension along which the universe, however vast, encounters limits. The limits are not walls, they are not fences, they are not cliffs at the end of the world. They are more subtle, more pervasive, and more interesting than any of those simple images. They are woven into the fabric of space-time itself, into the laws of physics, and into the structure of knowledge. And they are the reason that the question, simple as it sounds, has occupied some of the greatest minds in the history of science and continues to do so. In the end, the question is not really about whether there is a wall somewhere far away in space. It is about the nature of spatial extent, the nature of physical boundaries, and the relationship between mathematics, physics, and reality. These are questions that have been asked for millennia, in different forms and with different tools, and the answers have consistently been more surprising, more subtle, and more beautiful than the questions themselves suggested. The universe can be infinite and still have an edge, but the edge is never where you expect it, and it is never the kind of thing you imagine. It is always something stranger, something richer, and something that demands yet another revision of what you thought you knew about the world.